Now we're moving on to chapter 6. So let's do that. Chapter 6 is all about momentum. And we mentioned before the momentum and energy kind of have a little crossover with them. They're similar things, not exactly the same things. But one of the big similarities is that they have to do with mass and they have to do with velocity. Just slightly different to do. So here we have these great picture of these two cars colliding. And in this collision, we're not going to be conserving kinetic energy. There's just no way. Mechanical energy is going to be out the window because as these two cars collide, we have all kinds of crazy stuff going on. You can see that there's bending of the metal going on, there's braking of axles, there's airbags inflating, there's glass shattering, there's going to be a lot of noise, there's going to be heat in the metal. It's going to be a crazy amount of energy dissipation. So a lot of that kinetic energy is going to turn into just dissipated energy lost to the system. However, the momentum is another story entirely. So let's talk about momentum. Section 6.1, entitled Momentum and Impulse. So the first type of momentum we're going to study in this class is what we call linear momentum, or the momentum of objects that are linear motion. It's not necessarily that you have to be in linear motion to have linear momentum, but that's how we're going to approach it to make it nice and simple for us to start with. So linear momentum is the momentum that is associated with the linear motion of an object. We use the symbol P to denote the linear momentum, and notice that it is a vector. Again, we're back to vectors. We went into that energy section for a while, and we got rid of vectors, even though we had signs in the potential energies and so on. In the momentum, we're back to a vector. Momentum is definitely a vector. It has a direction, it has a magnitude, and so it has those two vector qualities about it. The definition of linear momentum is going to involve the mass and the velocity, like we said, and it's just mass times velocity. Very simple. You can see that it gets its vector trait from the velocity, since velocity is also a vector. And we're going to have units of kilogram meters per second. Now, nobody did enough work with momentum to earn the unit for momentum, so it's just kilogram meters per second. We don't use any special name for that. Also, since momentum is a vector, it can be split into vector components. So it can have an x component of your momentum, it can have a y component of your momentum, and here are the equations that would show that. It wouldn't be vector equations anymore. Well, we wouldn't show them as vector equations, even though they can be. But this entire equation would just be in the x direction. This entire equation would be in the y direction. We could split it up using the normal trigonometry kind of tricks that we've used before. The interesting thing here is that if you take the magnitude of the momentum, just that, the length of the vector or the strength of the momentum, which would be the mass times the magnitude of the velocity, and you take that and square it and then divide it by 2 times the mass, you will get kinetic energy. It actually has the same value as the kinetic energy. And so not only are they related because they both involve mass and velocity, but they're related because we can actually write an equation that relates the two, kinetic energy and momentum. But it only relates the kinetic energy to the magnitude of the momentum, not to the vector quality of the momentum. And that's important. Sometimes you may wonder, how do they know certain things are vectors and certain things are scalars? Scalar quantities, vector quantities, things that have direction for the vectors, things that don't for the scalars. That's a really good question. I don't know the answer. Actually, I do know the answer. But the answer comes from a lot of both mathematics and philosophy of these things. These early scientists that kind of made these distinctions and discovered these things were great philosophers, and they were able to decide that because velocity and acceleration behave the way they do, because of the way we've defined them, that they needed to have a direction associated with them so that we could talk about force, which definitely has direction. Whereas other things don't. And momentum is one of these things that has a definite need for a direction. And I think that that's probably more obvious to me when I start talking about rotational momentum, or angular momentum as it's called, and we will get to that later in this course. But momentum definitely does have a direction to it. It is a vector quantity. Momentum is also directly related to force, it turns out, and this is a biggie. It's really quite important in the physics world. So the force, the vector equation for force is force equals mass times acceleration. And of course we know that acceleration is equal to change in velocity over change in time. And we can actually write the change in velocity as the change in mass times velocity by pulling this mass inside of the delta, because the mass doesn't change, so it can go inside or outside the delta. For those of you who are calculus literate, this is like bringing a constant inside and outside of a derivative. It's totally legal, or inside and outside of an integral is also legal, because it doesn't change, it doesn't get affected by the calculus operators. But when you do that, then you end up with this delta mv, which is delta momentum, change in momentum. So the total force in a situation, total force on a system, for example, is equal to delta p over delta t, change in momentum over time. And this is actually Newton's second law in momentum form, and it actually can be quite useful. Remember before we said that that work is equal to a change in kinetic energy, and now we're saying that force is equal to a change in momentum. So now, impulse. What is impulse? Well, the impulse is actually defined as the change, as a force over a change in time, or if you rearrange this equation here, let's see, is that correct? No, that's the momentum. There's the impulse equation. So we've got to find the right equation for that. Oh, here it is. So the impulse is going to be defined as a force times a change in time. And we also know that a force times a change in time is a change in momentum. Okay, how do we know that? Well, up here we have a force is equal to change in momentum over change in time. And so we can actually just multiply both sides of this equation by delta t, and you get force times a change in time is equal to change in momentum. And so that's actually where they get this idea of impulse from. Impulse is essentially just a change in momentum. It's just defined as a change in momentum. It can be written as a force over a change in time, or a force that is applied during a time. Force times delta t, but instead of force delta t, force divided by delta t. You've got to keep that in mind. So it's force times delta t. And we define this as impulse, and this is called the impulse momentum theorem, because when you have a large impulse, you get a big change in this momentum. And a big change in momentum turns out to be bad in most cases. Again, this is going back to our boxer analogy. If a boxer gets hit with a particular change in momentum, he would prefer that change in momentum to happen over a long time with a small force. So it can be the same impulse, but a big time with a small force is the same as a big force in a small time. Big force in a small time makes a huge acceleration, however, and that's bad news. So they actually talk about that right here. So boxers, when they were first starting this fighting sport, was just fighting, and they would just punch each other with their bare fists. But when you're punching each other with bare fists, the impulse is over a very small time, and so it imparts a huge force. The same impulse is imparted to the head when you punch with the gloves on, except since the gloves are padded and it takes a while to compress that padding and for it to decompress, that time gets longer, and with the same amount of force, you get actually a smaller, the same amount of impulse, rather, the same change in momentum, you get a smaller force. Now let's take a look at that on Edukreations really quick. quick and see if we can make sense of that. So here is our equation. Our equation goes like this. We have force. It's hard to write on my mouse pad here. Force times delta time is the impulse. That equals the impulse. It's also equal to the change in momentum, right? Change in P. What happens when a boxer gets hit by somebody, by the same boxer 2 times in a row, same kind of swinging speed, same kind of swinging strength? The thing that happens is that this delta P stays the same, which means the impulse stays the same. However, if the person hits you for a very short time, like without gloves on, so this is without gloves, the fist makes contact with the face, it's bone on bone, and that it's a very small time, so you get a very small delta T, and you get a huge force times small delta T, right? Whereas if you're wearing gloves, it's the same impulse, so these two things are equal. It's the same impulse, except the gloves extend that delta T and make it a much bigger delta T, so that the force can actually be much smaller. So the amount of force is smaller. That means, since force is equal to mass times acceleration, your mass times acceleration is smaller. And the acceleration is the thing that does the damage, right? So, over here, of course, with the big force, you get a huge mass times acceleration times your little delta T, and that acceleration, well, the mass actually stays the same, it's the acceleration that gets big, but you get this huge acceleration that is just painful to the head, and sometimes just downright deadly. So, here's a great example of impulse. We have a golfer teeing off, right? He's not teed off, he's just teeing off. So we want to use this impulse momentum theory. Remember that impulse is equal to force times delta T equals the change in momentum. So what do we got? We've got a golf ball, has this mass of 5 times 10 to the minus 2 kilograms. So we have the mass. We strike it with a golf club, and the force on the ball varies from 0 when the contact is made up to some maximum value when the ball is maximally deformed. In other words, when you're first hitting the ball looks like a ball. When you're done hitting the ball kind of looks like a watermelon or something. It's kind of squashed. And then, as the ball comes off of the head at the end of the swing, the ball is deforming again, or reforming back into its spherical shape. Kind of wobbles around a little bit. And that deforming and reforming of the ball is what causes the time of the club on the ball. It's not a long time, but it is time. And in this picture, you can actually see the deformation of the ball. You can see that it's flat on one end, and actually it flattens out on the front end slightly as well. Not as much, but what we've got here, though, is that the ball leaves the club face with a velocity of 44 meters per second. Now that's important because that's going to tell us our final momentum. Whereas our initial momentum, since the ball wasn't moving at all sitting on the tee, was 0. And so the impulse momentum theorem is quite simple. It's the impulse equals the change in momentum. Change in momentum is momentum final minus momentum initial. Now since we're in one dimension here, it's just the ball going straight forward. We're not using vectors, we're just using the magnitudes. And momentum final is going to be the 5 times 10 to the 2 kilograms times the 44 meters per second. The initial momentum will be 0. And our impulse is now 2.2 kilogram meters per second. Now to calculate the time of the collision between the ball and the club head, we use this change in momentum as in the impulse theorem again, or in the impulse equation again, to let's see, is that what they're actually doing? They're saying estimate the duration of the collision and the average force acting on the ball. Okay. I guess we can do it that way. Okay, so what they're doing here is they're using just the equation for the velocity average, which would be distance over time, and they're solving it for time. So you have delta x over delta t and v all here. And so if you solve that for time, you get delta x over v equals delta t. And what they're saying is that the interval of the collision, or the distance of the collision, is actually going to be about half of the ball, or the radius ball. So it's about 2 times 10 to the minus 2 meters is that distance. And then the velocity is 22 meters per second, they're saying here. And they're saying how much time does that take? 9.1 times 10 to the minus 4. And then they want us to estimate the average force from equation 6.6. And this equation 6.6 says that the force times delta t equals delta p. So we solve that for, well, actually this is delta p over delta t, but anyway, this is impulse when we multiply both sides by t, right? By delta t. So this is actually the same equation as up here. It's just rewritten and rearranged a little bit. But we take that change in momentum from part A divided by the time interval in part B. We get 2.4 times 10 to the 3 newtons of force, which is pretty substantial. 2.4 times 10 to the 3 is twice what I weigh in just that very, very short time frame. Just a few milliseconds, really. So have you ever wondered why cars are designed to crumple up, or did you even know that? Well, the first car that became famous for having what we call crumple zones today is probably a Volvo company, and they're actually showing a Volvo here in this crash test. It was designed specifically to break and bend and crumple up and make noise and everything else while you crashed, and the idea is that you lengthened out the time of that collision. You lengthened out the change in momentum so that you could have a very small force imparted to the driver, which would hopefully save their life. So here we have this kind of a problem where we have a bumper in a car designed to do just this, and here they're showing, of course, a car that looks like a Prius. Ugliest car ever made, but oh well. I hope nobody drives a Prius. I wasn't meaning that personally. But we have a crash test. The car has a mass of 1.5 times 10 to the 3 kilogram, collides with a wall, rebounds. The initial and final velocities of the car are velocity initial is negative 15, so it's going left. And then the final velocity is 2.6, and that's positive going right. So we have an initial and a final velocity. We can use those to calculate a change in momentum. And then they tell us that the collision lasts for 0.150 seconds, 150 milliseconds. And so we can use that change in time to calculate the force. So A, we want to calculate the impulse, and then B, we want to calculate the size and direction of the average force exerted on the car. We have to be very careful when we're doing this part because signs are important, directions of velocities and everything else are important because this is a vector equation. So the impulse delivered to the car is going to be, we want to calculate the initial momentum. That's just mass times velocity initial. The sign is important. Final momentum, mass times velocity. Sign is important. We've got a negative momentum, we've got a positive momentum. Then we're going to take the final momentum, subtract the initial momentum, and when we get the overall change in momentum, that's going to be equal to our impulse. So our impulse is 2.64 times 10 to the 4 kilogram meters per second. Then, in the equation where we have force times delta t equals delta p, we can solve that again for the force and calculate that average force. The change in momentum, which we have up here, 2.64 times 10 to the 4, because that is the same as the impulse, divided by the change in time, which was the 150 milliseconds, is 1.76 times 10 to the 5th newtons. So a fair amount of energy imparted there. In this last section, they talk about the injuries when you're in a car accident. So here it says, if a collision lasts for less than about 70 milliseconds, a person will survive if the whole body impact pressure is less than 1.9 times 10 to the 5th newtons per meter squared. So they're talking about pressures here, which we haven't really covered yet. But you can see that they know how much force you can absorb, or how much force you can undergo and survive. And that's exactly what they're going to do here. So you're going to calculate the average force when a car changes in momentum, or no, actually, so a person not wearing a seatbelt hits a unpadded dashboard, and they change their momentum in a certain amount of time, and they get negative 2 times 10 to the 5th newtons of force, and It turns out that that's very dangerous because they get an acceleration of 280 g, 2,700 meters per second squared. That is deadly force. Okay? You'll break every bone in your face and your neck and your back and everything else, and your brain will be squashed in 1,000 pieces. And that's not even going that fast. I mean, how fast are we talking about here? We're talking about 27 meters per second is all. You're going from 27 meters per second to 0, 60 miles an hour. In fact, it also stays lethal if you're only going 25 miles an hour. You go 25 miles an hour and stop from 25 miles an hour to 0 by hitting something that is stationary that won't move, and you will die if you are not seatbelted in. Because the acceleration with your head and the windshield or your head and the dashboard is just too much for you to handle as a human being. So, this is what happens in a collision with a car here. They have this nice graph here where it shows this is time in milliseconds. In the first 40 or 60 milliseconds, the force is down in the 4 times 10 to the 5th, which is still deadly. But when you get into the kind of the meat of the collision, it's 8 times 10 to the 5th. You're gonna die if you absorb that in your head and your neck. That can be absorbed by your chest much better, even though it won't feel very good. You'll have bruises and maybe break some ribs. And with an airbag, it makes it even better because it lengthens out the time of the collision. With the airbag slows you down over a much longer period. Same amount of impulse, but a much smaller force over a longer time, a bigger time. So it becomes a big issue. Okay, so that is 6.1. Let's go take a look at the homework really quick, and then we'll end this session. So 6.1, am I in the right class? No, I'm in the wrong class. All right, let's go to the right class. So Physics 1410. Let's take a look at homework 6.1 and see what we think. Okay, we've got 6 problems. Linear momentum, we're calculating the magnitude. You've just got a mass, you've got a velocity, it's plain and simple. Interesting to look at some of these momentums and compare them, just kind of see what's going on. Pitcher claims you can throw this baseball with as much momentum as a bullet moving at this speed. And we want to see how fast that pitch must be, right? Which has the greater kinetic energy. Well, what must the baseball speed be if the pitcher's claim is valid? They don't even ask us if the pitcher's claim is valid, but if it's over about 50 meters per second, then it's invalid because that's over 100 miles an hour. Not many people can do that. A ball of mass m is thrown straight up in the air. We want to find expression for the maximum height reached by the ball, and using conservation of energy, find the magnitude of the momentum of the ball at 1/2 its maximum height. So what you're going to do, you can use conservation of energy to calculate the velocity of the ball at the halfway point, and then use that velocity to calculate momentum at the halfway point. We have an estimated force versus time curve, and force versus time is, force times time, of course, is momentum. So we're counting squares under the curve again. Counts the area under the curve is going to be the change in momentum, or the impulse delivered to the ball. And then we have a volleyball player. Of course, I had to put this in because I love volleyball. In this one, you have this, let's see, the player strikes the ball with her fist and causes the ball to move in the opposite direction. So we have a ball that is, let's see, so we have a ball that's moving towards the player, and then the player hits the ball in the other way. And that's important because one of these is going to be a negative direction. One of them is going to have to be positive because they're going in opposite directions. And momentum is a vector quantity. So you have to write one of these as a negative, one of them as a positive, and to calculate that change in momentum as final minus initial. And then calculate the momentum from that and the impulse. And then you have a tutorial exercise at the end. And I'll let you go ahead and do it. So I think that you should be able to get those. The only two that are really tough, I think, are the last or maybe 4 and 5, not 4 and 5, 3 and 5, where 5 you have to realize that little trick of momentum directions, and 3 you have to use kinetic energy stuff from chapter 5 to get the velocity halfway up. But again, you just finished doing chapter 5, so hopefully that won't be too hard. All right, that's all I've got for you today. I hope that you have a great day and enjoy. I will be available if you have questions, so please send me an email, give me a call, leave a message. Have a good one.